Welcome back. In the previous video, we learned about reflection and how that phenomenon has to do with mirrors and different types of mirrors, plane mirrors, spherical mirrors. We want to move on to the next phenomenon of light and waves and how they interact with media, and that's refraction. Refraction has more to do with lenses. So, reflection is to mirrors as refraction is to lenses. The lens talk is a little bit longer than the mirror talk, so I'm going to break this video up into a couple. And in this little shorter one here, I want to talk about the phenomenon of refraction and then Snell's law specifically, and then we'll come back and do a separate one on lenses, using the lens equation. All right, so let's begin with a definition. As you can see on the screen, refraction has to do with the bending of light waves, and really this would apply to non-light waves as well. But we're talking about light most of the time in these lenses and, well, all the time in these lenses and mirror type problems. But anyway, when waves enter a new substance, they will bend at the barrier. And the reason is the energy that's traveling in the form of a wave is going to interact differently with the particles depending on how closely or far apart they're spaced together. In the last video, I told you about the normal. Remember, the normal is always perpendicular to a surface, so straight up and down. So when this light ray enters this new medium that's passing through here, if that is a more dense substance, you're going to see the light bend toward the normal. And let's go ahead and extend that normal straight on through here. So it'll be bending toward the normal. And if it entered into a medium that was less dense than the one it was already in, then it would bend upwards away from the normal. So refraction is the bending. Now, let's go through a little bit of some of the relationships here. So the relationship between the incident ray and the refracted ray can be modeled using Snell's law. All right, so Snell's law is all about refraction. In the very middle of your screen here, you'll see the Snell's law. It just says it's a proportion. N is what you're going to call the index of refraction. We'll go through where this comes from in just a moment. And then the thetas here are going to be your angles, remember, in relation to the normal, not the surface, to that perpendicular normal. At the very bottom of the screen here, we see some common indices of refraction. So we say that a vacuum would have an index of refraction of 1. So N1, or when N equals 1, that's quote-unquote normal. For air, since the particles in air are pretty far apart, you don't have much interaction or much hindrance to light traveling, the index of refraction is about 1. It's going to be a little bit more than 1, but not appreciably much at all. But you can see as we get into denser substances like water, the index of refraction does end up changing quite a bit, 1.33, and then as we get into glass or diamond, 2.42. So here we have a ray of light traveling through air, incident, remember that's incoming, upon a sheet of crown glass at an angle of 30 degrees Celsius. What is the angle of refraction? So as the light passes into this glass, is it going to bend toward the normal, so downward, or is it going to bend kind of upwards away from the normal? So all we do for this is plug in. We have air. So remember, N for air is 1. We're going to plug into 30 degrees. Remember, the incident angle is always to the normal as well. And then we're going to divide that by N2, solve for theta, and get 0.329. Now we have to take the inverse sine of that. So that's just on your calculator, second sine function nowadays. It's pretty simple. And we get an angle of refraction of 19.2 degrees, again, to the normal. And that is a smaller angle than 30, so what that's showing you is the light is bending toward the normal. Let's look at a diagram here and kind of get an idea of where these N values come from. So here I have a couple of parallel rays. And on ray X here, near any given time interval, you have a traveling from B to A for ray X, and then from C to D. Okay, so notice these are in different materials. One's in, I guess, air, and one of them's in water or crown glass or whatever. The ratio of the BA to CD is going to be the same as the ratio of the speed of light in one of those substances to the speed of light in the other substance. And since for the index of refraction we use the speed of light in a vacuum, so what we end up getting is an expression to find or define the index of refraction. So here is how we would actually calculate a very specific index of refraction. All we need to know is the speed of light, which is a constant, and then if we could somehow measure the velocity of the light traveling through any other medium, we can really quickly calculate that index of refraction for that substance. So we would have to use some experimental physics to do that. You're not going to be asked to do that, but you could be asked a question where it just says the speed of light, it takes, I don't know, 20 microseconds for light to travel 2.5 centimeters. So what is the index of refraction for this material? So you would use your physics, calculate the velocity given that time and distance, and then you use this formula right here and divide that into C to get your index of refraction. So that's possible. You could do that. So here's another example. The index of refraction of water is 1.33. So calculate the speed of light in water. I want you to hit pause and do that calculation on your calculator real quick. All right, so you just plug in here. We know that we got rearranging the equation to find the water. Oh, sorry. So we're just going to rearrange this equation here, reorganize my variables to get the velocity of the light in water. So we're going to divide C by the index of refraction. So plugging in our numbers here, speed of light divided by the 1.33, the velocity of light traveling through water, 2.26 times 10 to the 8th meters per second. So not that bad. It's still, you only lose a little bit, a small percentage of the speed of light as you travel through water. Okay, so one phenomenon that occurs to this is if you're shining a light on a surface, a glass or something that you're trying to pass it, water, wherever you're trying to pass it through, how does the angle affect what you see? So in the previous example, we were just shining it kind of at 30 degrees and it refracted, that's fine. But a logical question that comes to this is there an angle that I can shine the light at where I don't see anything come out the other side? So does the ray might seem to get lost in the new surface? And the answer to that is yes. You can actually calculate an angle that if you shine light at that angle, it would never exit the new substance. We call that total internal reflection, and the associated angle there is called the critical angle. All right, so here's an example. Light inside a diamond hits the boundary to air at 60 degrees Celsius. 60 degrees. What is the angle of refraction? All right, so using Snell's law here, we're looking for the exiting angle. So we're going to set up, resolve, and try to calculate theta 2. Let's plug in our numbers here. 1.52 sine of 30 over 1. I'm looking at that calculation. I need to go back and check. I think we had a different number for the index of refraction of diamond here. I'll go back and check that after the video's over. But at any rate, it comes out to be 1.31. So let's just pretend these numbers are right, even though I have some suspicions about that. Let's assume that's right for now, and this is the number we get, 1.31. So let's take the inverse sine of 1.31, and the calculator tells you it's an error. So this is a case where you have total internal reflection. If these conditions are all correct, and this were the index of refraction for diamond, and you shine it at 30 degrees, then you're not going to be able to get the ray of light exiting the diamond. You have total internal reflection. Now we could also calculate that critical angle. The critical angle specifically is the one where the refracted ray goes 90 degrees. Now why is 90 degrees important? Well, remember, we're taking everything in reference to the normal, which is perpendicular to the surface. So if you go at 90 degrees to the normal, that means you are parallel to the surface and you will never exit the surface. So let's find the critical angle of diamond. So rearranging here, we're looking for the angle. We're going to plug in our values. 1 comes from air or a vacuum, either way. And then we want to know the critical angle, so we have to know that it's coming out at 90 degrees, and then we're dividing by the 2.52. So yeah, so that previous problem had an issue on the index of refraction. But anyway, let's get this theta here. It comes out, sine of theta 2 equals 0.39. So let's take the inverse of that, and we get 23.4 degrees. So if I shine light here for diamond, 23.4 degrees is the magic angle to where I get a perfectly horizontal parallel ray of light. That's the critical angle. All right, so we're going to use this to solve some lenses in the upcoming video. So let us know if you have any questions about refraction.